And welcome to Lecture 6. Last time we left off saying that we would look at the enthalpy change for this particular reaction, making acetylene, and see if it made sense. It was 226.7 kilojoules per mole. First off, I want to emphasize that it's positive 226.7 kilojoules per mole. Now, when an enthalpy change is positive, that means that energy is being stored inside the chemical bonds of the products. Okay, the products are at a higher energy. They're at a higher chemical potential energy than the reactants. In order to make those bonds, you've had to sort of elevate. You've lifted this molecule up off the ground. Does it make sense to say that acetylene is a place to store energy? For those of you who don't know, acetylene is what they use for welding. Okay, it's a carbon-carbon triple bond. So yes, it is a very high chemical potential energy. So hopefully that makes sense compared to the real world. Now let's go ahead and look at our reactions up above. The building blocks that we made this out of. Does it make sense for it to be an endothermic reaction in light of those three reactions? Let's look at reactions 2 and 3 first. Those are just the combustion of carbon and hydrogen using oxygen, and those both release energy. That makes sense. But the first reaction is the combustion of acetylene. Okay, when you combine acetylene and oxygen to make carbon dioxide and water, the reaction as it was originally written, it released a ton of energy. It released 1,300 kilojoules per mole. Now, of course, we've flipped it around so that instead of combusting it, we're anti-combusting it to make acetylene out of CO2 and water. And so it absorbs 1,300 kilojoules per mole. So does it make sense that burning acetylene would release more energy than burning raw carbon and hydrogen? Well, yeah, because acetylene has that carbon-carbon triple bond. It's a sink. It's an energy sink. It's a place to put a lot of energy. Okay, so by comparison, making acetylene out of CO2 and H2O takes more energy than you get by making carbon dioxide and water from the elements carbon and hydrogen. Okay, so that is what those numbers are telling us in the way that we've written those three equations. When you rearrange and flip around and multiply these three equations, those are the numbers that you get, and the result is that we see that, as you would expect, making acetylene out of elemental carbon and hydrogen is an endothermic reaction. Now, I know that this doesn't necessarily come naturally to anyone, so let's go ahead and work another example of a Hess's law problem. This time we are going to do something that might be a little counterintuitive, except for the fact that it looks an awful lot like the first example I gave you. Basically, what happens, or can you get information about carbon and oxygen combining to form CO2 by playing around with strontium oxide, strontium metal, and strontium carbonate? The answer is yes. So this looks really complicated, but it's not as awful as you might think. Let's just remember, you want the things up top to eventually add up to the goal down here at the bottom. So let's see if we can't find something that only appears in one reaction. Well, we have carbon. Down in reaction 3, carbon appears among the products, and it does not appear in either of the other two reactions. However, there's a little bit too much carbon. There are 2 carbons on the product side. We need 1 carbon on the reactant side. So we're going to need to flip this reaction around. That means that we're going to multiply it by a negative number. And we need to get that 2 to turn into a 1. So we're going to need to multiply by 1/2. So flipping it and reducing it means overall multiplying by negative 1/2. And, of course, whatever we do to our reaction, we also have to do to the enthalpy change for that particular reaction. And the end result is that we end up with reaction 3 turning into strontium plus carbon plus 3/2 oxygen yields strontium carbonate. And negative 1/2 enthalpy change 3 is equal to negative 1220 kilojoules per mole. The remainder, we have things appearing in multiple equations. It looks fairly unpleasant, right? Well, we can still sort things out. You might be tempted to go running up on oxygen and take care of that, but oxygen appears in reaction 2 and reaction 3, and we need to have oxygen left over down at the bottom. So let's put oxygen on the back burner for a second and just focus on strontium. Strontium doesn't show up in our goal reaction. We want to get rid of strontium. It only appears in reactions 2 and 3, and it's on the reactant side of reactant 3. It's on the product side of reaction 2. So if we can get the number of strontium on the product side of reaction 2 to be the same as the number of strontium on the reactant side of reaction 3, it'll cancel out and it'll go away. And hopefully when we're done with that, then it'll leave us with stuff we can work with moving forward, and maybe it will also deal with oxygen. Let's take a look at what happens. Reaction 3 has 1 strontium. Reaction 2 has 2 strontium. So we're going to go ahead and multiply the entire thing by 1/2. Reaction 2 gets multiplied by 1/2. That means that when we have done that, it is going to be 1 strontium oxide yields 1 strontium plus 1/2 oxygen. And that is also going to multiply the enthalpy change for reaction 2 by 1/2, leaving us with 1/2 enthalpy change. Reaction 2 is equal to positive 592 kilojoules per mole. And finally, we take a look at reaction 1. We have pretty much a number of ways to move forward here, but let's go ahead and look at carbon dioxide. Carbon dioxide only shows up in reaction 1, and we need it to show up in the products down there in our goal. And it shows up in the reactant side of reaction 1, which means we need to flip the reaction. Carbon dioxide isn't the only thing you can look at here. You can also look at strontium carbonate. Strontium carbonate is on the product side here, but we need to cancel out the strontium carbonate that shows up on the product side way down at the bottom in reaction 3. So we need to get that on the reactant side. And those are both good arguments for multiplying the entire thing by -1. You can make a similar argument for strontium oxide. It needs to be on the product side in order to cancel out the strontium oxide down in reaction 2. In any event, you flip the reaction, you multiply it by -1, you're going to get strontium carbonate yields strontium oxide plus carbon dioxide. You're also multiplying the enthalpy change for reaction 1 by -1, which means that now we have an enthalpy change of positive 234 kilojoules per mole. Before we go ahead and find our final answer, let's go ahead and double check that everything cancels out like we need it to. Okay, so we lose all that strontium garbage, and we just end up with carbon, oxygen, and carbon dioxide. First thing first, let's get rid of that strontium carbonate. Okay, there's 1 strontium carbonate on the reactants in reaction 1. There's 1 strontium carbonate among the products in reaction 2. Gone. Strontium oxide is going to disappear next. There's 1 strontium oxide in the products of reaction 1. There's 1 strontium oxide in the reactants of reaction 2. And those cancel out and disappear. And finally, we have 2 more things to do. Our penultimate elimination, our quarter finalist, is going to be strontium. There's 1 in reaction 2, and 1 in reaction 3. And then our final elimination is going to be the 1/2 oxygen in the products of reaction 2. There are 3/2 oxygen in the products of reaction 3. You do a little bit of arithmetic, and 3/2 minus 1/2 leaves you with 1 oxygen among the reactants in reaction 3. And now we look at everything we have left, and we see that 1 carbon plus 1 oxygen yields 1 carbon dioxide. Our 3 building block reactions add up quite nicely to our goal down there at the bottom, which means that our enthalpy of reaction is negative delta H1 plus 1/2 delta H2 minus 1/2 delta H3 for a total of negative 394 kilojoules per mole. And does that make sense? I should hope so. It's an exothermic reaction, and yes, burning carbon is going to be exothermic. That's why we do it. Now, why do we give a damn about Hess's law and all this stupid work? Say you have a reaction, just any sort of reaction, A going to B. Well, it might be the case that for some reason you cannot get from A to B directly or easily. Say you have methane going to methanol. It would be nice if we could convert methane to methanol directly, but we can't. When you actually do that, methanol is more stable than methane, or I should say it's easier to transport, not more stable. It's easier to transport because it's a liquid, whereas methane is a gas. Thus, people would very much like to be able to make that conversion, but they can't. And that's why when you see oil wells, with the big flames coming out the top, they're burning off methane that cannot be transported safely or easily. But trying to make that conversion, the chemicals you have to use, they just keep on going, and they keep on working, and they convert methanol into carbon dioxide. It just doesn't work. So that's just one example of why you might not be able to get from A to B. So you can't measure the enthalpy of reaction directly. But perhaps you can use a more indirect route. What if, to pick something completely at random, you converted your methane to glucose and then converted your glucose to methanol? I personally don't know of any method for doing that, but there could be something like that out there. I do know that this is an avenue or a field of active research in fuel cell technology, because methanol is not just easier to transport than methane, it's also a heck of a lot safer than hydrogen, as well as being a nice, dense energy storage medium. However, the fact is that picking random intermediaries for every reaction you care to look at isn't all that great. So, wouldn't it be nice if we had some sort of standard set of intermediaries that you could work with? Why, yes it would. And since we're at about 15 minutes, I'm going to go ahead and quit this lecture. When we come back, we will pick this back up talking about the standard enthalpy of formation.